This video I am going to talk about unsymmetrical fault analysis by using symmetrical component method. What is unsymmetrical fault? The fault current in a three phases are unequal. That type of fault are called unsymmetrical fault. There are three ways in which unsymmetrical fault may occur in a power system. The three ways are single line to ground, line to line, double line to ground. Then single line to ground fault. Any one of the line breaks and contact with ground, or in a generator, one phase line insulation is failure and the phase winding is touches with the metal body. It's make a contact with ground. That is called single line to ground fault. Or one tree is touches with a single line, means a current will flowing through the tree medium to ground. That is single line to ground fault. Then line to line fault. The two lines are touches together. It makes a line to line fault. This will happen one line break and touches with another line, or any tree branch or animals like snakes are crossing these two lines make line to line fault. Then double line to ground fault. The two lines are breaks and touches with ground. Here this type of faults are called unsymmetrical fault. That means the fault current in the three phases are different, not equal. So this fault is called unsymmetrical fault. These type of faults are analysis through two methods, Kirchhoff's law method or symmetrical components method. The Kirchhoff's law method is applicable for only small type of system. In case of large type of system, means the calculation is very tedious process, complicated. So the second method is preferable. The reason for preferring the second method is it is a simple method. Then it provides a useful tool for protection engineer, particularly in connection with find out fault currents. Now let's see symmetrical components method. This is the one mathematical method. The standard definition of the symmetrical components method is an unbalanced system of n related vector can be resolved into n system of balanced vectors called symmetrical components of original vectors. According to this definition, n unbalanced vectors, that is the magnitude and the phase angle of the vectors are different, that vectors are resolved into a symmetrical components of vectors. The sum of the symmetrical components of vector is equal to the unbalanced vector. Now we are going to find or calculate the symmetrical components of vectors. We know the symmetrical components of vector means just add these vectors, get the unsymmetrical components of vectors. In case of power system, the unsymmetrical components of vectors, the voltage vectors are VA, VB, VC. Then current vectors are IA, IB, IC. Here the phases are taken as A, B, C. Usually the phases are RYB. Here in our calculation, we take A, B, C. These are the unbalanced voltage vector. Because a fault occurring in a power system, the unsymmetrical fault occurring in a power system, the fault current in the three phases are different, as well as the voltage in the three phases are different. Also the phase sequence also different. So the voltage vector length are different, the phase sequence also different. This is called the unsymmetrical vector. This unsymmetrical vector is resolved into a symmetrical components of vectors are called positive sequence component, negative sequence component, and zero sequence component. The sum of this sequence component is called the unsymmetrical component of vector. Add these three sequence components vectors, get the unsymmetrical components of vectors. What is positive sequence component? The positive sequence component consists of three vectors in equal magnitude and displaced from each other by 120 degree in phase and having same phase sequence as that of original vector. Here it consists of the positive sequence vector diagram. Here consists of three vectors VA1, VB1 and VC1. One indicate positive. The magnitude of these three vectors are equal. VA1 is equal to magnitude of VA1 is equal to magnitude of VB1, that is equal to magnitude of VC1. And also the phase angle difference between these vectors are 120 degree. Then the phase sequence, that is the order. Here the original vector order is ABC. Here also ABC. The phase sequence is same as that of the original vector. That is called the positive sequence component. Then next one, the negative sequence component. What is negative sequence component? The negative sequence component also consists of three vectors equal in magnitude, displaced from each other by 120 degree in phase, and having the phase sequence opposite that of the original vector. Here also the magnitudes are same. Here the 2 indicates the negative sequence. VA2 is equal to VB2, that is equal to VC2. The magnitude of these three values are equal and the phase angle difference between these vectors are 120 degree. The phase sequence is ACB. Here the actual phase sequence is ABC. That is the opposite that of the original vector. Then next is zero sequence component. What is zero sequence component? It also consists of three vectors equal in magnitude. Zero place displacement from each other. That is the phase angle difference between these vectors are 0 degree. The magnitudes are same. Magnitude of VA0 is equal to magnitude of VB0, magnitude of VC0. So here there is no phase sequence. All the vectors are coincident one another. Operator A. Rotating one vector by anti-clockwise direction 120 degree, get another vector. That is called the operator A. An operator A which causes a rotation 120 degree in anti-clockwise direction is denoted by the letter operator A. So the value of A is 1 angle 120 degree. This is in polar form. This is converted into rectangular form, get minus 0.5 plus J 0.866. Then again rotated means get 240 degree. A square is equal to 1 angle 240 degree. A into A. A into A, 1 angle 120 degree into 1 angle 120 degree, get 1 angle 240 degree. It's taken as A square. The rectangular form minus 0.5 minus J 0.866. Then A cube, 1 angle 360 degree, that is equal to 1. The sum of these values, A plus A square plus A cube value is equal to 0. The rectangular side add this value, get 0. Then I already told original unbalanced vector is the sum of positive, negative and zero sequence component. For example, here VA is equal to positive sequence voltage VA1 plus VA2 plus VA0. Similarly, VB is equal to positive sequence, negative sequence and zero sequence voltage. Now rotating the vectors, the multiples of 120 degree in anti-clockwise direction, get another vector. Now consider the positive sequence network. Here rotating the VA1 vector in 240 degree, get VB1 vector. 240 degree is A square. So VB1 is A square into VA1. Now let's rotate the VA1 120 degree in anti-clockwise direction, get VC1. VC1 is equal to A into VA1 because A is equal to 120 degree. Then consider the negative sequence network. Here also in negative sequence network, the VA2 is rotated 120 degree, get VB2. So VB2 is equal to A into VA2. Then rotate 240 degree. That is A square into VA2 is equal to VC2. VC2 is equal to A square into VA2. Then here in case of zero sequence network, here all the vector magnitudes are same. Here there is no phase angle rotation. All vectors are coincident together. So VA0 is equal to VB0, that is equal to VC0. So VB0 is equal to taken as VA0. Similarly, VC0 is taken as VA0. Substitute these conditions in this equation. We get the new equation. VA is equal to VA0 plus VA1 plus VA2. Then VB is equal to VA0 plus, in the place of VB1, substitute A square into VA1. Then VB2 place, substitute A into VA2. Then in the last equation, VC is equal to VA0 plus in BC1 place substitute A into BA1, BC2 place substitute A square into BA2. Get this equation. Now write this equation in matrix form. BA, BB, BC is equal to 1, 1, 1, 1 A square A, 1 A square, BA naught, BA1 and BA2. This is the unsymmetrical components of voltage in terms of symmetrical components of voltage. Suppose the symmetrical components of voltage values are known, means by using this matrix, calculate the unsymmetrical components of voltage. The unsymmetrical components of voltages values are known or given, means calculate the symmetrical components of voltage by take this term left hand side, that is cross multiply this term and take inverse. Take inverse, get this one 1 by 3, 1, 1, 1, 1 A square, 1 A square A. This is the unsymmetrical components of voltage in terms of unsymmetrical components of voltage. These two voltage equations are important. Similarly for current matrix, the current unsymmetrical vectors are written like this. Here in this previous matrix, replacing V by I, you get unsymmetrical components of current vector. IA, IB, IC is equal to 1, 1, 1, 1 A square A, 1 A square, IA naught, IA1, IA2. Then in this equation, replacing V by I, get the symmetrical components of currents. IA naught, IA1, IA2 is equal to 1 by 3, 1, 1, 1, 1 A square, 1 A square A. In the place of B, here I substitute I, get IA, IB, IC. These four equations are important equation. Then sequence network and sequence impedance. Let Z1 positive sequence impedance of generator, Z2 negative sequence impedance of generator, Z0 zero sequence impedance of generator, including neutral reactance. Now let's draw the positive sequence impedance network for the generator. What is positive sequence network? Positive sequence network is nothing, that is the per unit reactance diagram. The per unit reactance diagram of generator is the voltage source behind a reactance or impedance. Here this is the positive sequence network or per unit reactance diagram of the generator. Here all marked values are positive sequence value. Z1 positive sequence impedance, then BA1 positive sequence voltage, then IA1 positive sequence current. Here in this circuit, applying Kirchhoff's voltage law, get the voltage equation. Here BA1 is equal to EG minus drop IA1 into Z1. The next, negative sequence network. The voltage sources are removed, get the negative sequence network. Here this is the negative sequence network. Here marked values are negative sequence values. 2 indicates the negative sequence is Z2 negative sequence impedance, IA2 negative sequence current, BA2 negative sequence voltage. Here also applying Kirchhoff's voltage law, get BA2 is equal to minus IA2 into Z2. Then zero sequence network. The zero sequence network is depends on grounding. The grounding is solidly grounded or neutral grounded or ungrounded. The zero sequence network diagram varying. Here consider this diagram grounded through the reactance. Here this Z0 indicates Z0 is Zg0 plus 3 into Zn. Neutral is grounded through the reactance. So Zn is equal to, Zn is the neutral reactance. So the Z0 is equal to Zg0 plus 3 into Zn. Here in this circuit, the marked values are zero sequence component. Z0 is the zero sequence impedance, IA0 zero sequence current, BA0 zero sequence voltage. Here also applying Kirchhoff's voltage law, get BA0 is equal to minus IA0 Z0. Here these three equations are written in matrix form. We get BA0, IA1, BA2. This is in left hand side. Then here there is no voltage generation term, 0. Here second EG, then third equation 0. Then minus Z0 0 0 0 Z1 0 0 0 Z2. Here this coefficients, current coefficient IA0, IA1, IA2. These three equations are written in matrix form. Get this equation. This matrix equation is called sequence network equations. Totally, these 5 equations are important equations. 5 equations are: first one, the unbalanced voltage equation; second one, unbalanced current equation; third one, balanced voltage equation; fourth one, balanced current equation; then last one is the symmetrical components network matrix equation. By using these 5 matrices, we can easily solve the unsymmetrical fault, like single line to ground fault, line to line fault, double line to ground fault.